So I just want to remind you here that we've solved inequalities before. We solved them at the end of chapter 4, excuse me, and we solved inequalities that involved quadratic functions. So just as a reminder, one of the techniques we used in that section was we got 0 on one side of the inequality, and then we graphed the quadratic function. We found the x and y intercepts, and we identified where the graph was above or below the axis. So quick reminder, here was a problem from 4.5 that we did. We solved this quadratic inequality. And then we noticed we had 0 on one side, so we graphed this whole parabola here. And we saw that parabola, and we found the x-intercepts in particular were of interest to us. So we talked about the fact that if we were solving this quadratic less than or equal to 0, we were looking for where the graph was below the x-axis, right, where the y values were negative. Y values were less than 0. So, right, so that was this piece of the graph here. So we're looking for the y values were negative. That was this piece of the graph that in this case turned out to be between the x-intercepts. So if I pick any value, suppose x equals 4, I get a y value that's negative, and that's going to satisfy this inequality. If I pick anything to the right, like x equals 7, I'm going to get a y value that's positive, and that's greater than 0, not less than or equal to 0. So we did a very visual way of solving inequalities in 4.5. And for this particular example, to finish it off, we would say any x between -2 and 6 were solutions to this inequality. So we could graph that way, and because we had the or equal to here, we put brackets and included the endpoint. You know, we could do it as an inequality, or we could do it in interval notation. So a real quick review of what we did back in 4.5 solving quadratic inequalities. And the reason I wanted to bring this up is because we're going to basically be doing the exact same thing in this section, except we're going to be dealing with polynomials and rational functions instead of quadratic functions. So let's take a look at a polynomial example. Before we do that, the book points out to you pretty much what we just reminded ourselves of, is that we're going to always want to get 0 on one side. That's going to make things so much easier for us to approach it that way, because then we can find where it equals 0 in either of these cases, and those are our x-intercepts, and then we can look where the graph is either above the x-axis or below the x-axis when we solve those inequalities. Okay, so a couple examples here. So suppose here's the inequality we want to solve. Now the first thing I'm going to do is subtract the 4x squared to the other side so that I can get 0 on one side of this inequality. Right? So that's what I do. And then the next step is going to be to find where this polynomial, or we have a 4th degree polynomial here, find where it's equal to 0. So I'm going to find the x-intercept. Excuse me. So I set it equal to 0. I'm going to factor the x squared out. And then I could factor this further. This is x minus 2 times x plus 2. And I get the 3 zeros for that polynomial. Okay. Now the next piece would be to split the number line based on those x-intercepts. So this is similar to what we did with graphing rational functions. We're going to split up the number line. We're going to plot all of our x-intercepts here. And then I'm basically going to pick a number in this interval and see if it satisfies the inequality. I'm going to pick a number in this interval, I'm going to pick a number in this interval, and I'm going to pick a number in this interval. So really similar to what we did with graphing rational functions where we were plotting extra points. And so we're going to select a number in each interval and evaluate the polynomial. Right, so in this interval over here from minus infinity to minus 2, I chose x equals -3. And I'm plugging it into my original, into the polynomial x to the 4th minus 4x squared. And that's what I'm plugging into. So if I plug this into x to the 4th minus 4x squared, I'm going to get 45 out of that as a result. And I'm just pointing out to myself that that's positive. And then again, if I jump back to the prior slide, right, the reason I'm pointing out to myself that it's positive is because I'm looking at this polynomial and I want it to be negative, less than 0. So I'm going to note to myself that it's a positive value, and then that's not of interest to me in this case. Excuse me. All right, so then we'll do the next interval. So the next interval is between -2 to 0. So in that interval, I'm going to pick x equals -1 right here. And if I plug -1 into the polynomial x to the 4th minus 4x squared, I'm going to get a y value of -3, and that's negative. Right? So that's less than 0. That's going to be of interest to me in this case. So now I keep picking numbers here, right? So I'm going to pick a number between 0 and 2. So in this interval, I'm going to pick x equals 1 right here. If I plug 1 into my polynomial, x to the 4th minus 4x squared, I get a y value of -3. And then point out to myself that that's negative. And then in the interval from 2 to infinity, right, to the right of that last x-intercept, I'm going to pick x equals 3. And I'm going to plug that into my polynomial, and I get a positive value. All right, now if we look visually, right, here's the graph of my polynomial. So here's my x-intercept at -2. Here's the x-intercept at 0. Here's the x-intercept at +2. Right? And just to point out to you, right, remember x squared had an even multiplicity, right? The x-intercept at x equals 0 came from the factor x squared. So it had a bouncing behavior there, had an even multiplicity, right? So this graph matches, right? If we were to go through the steps of graphing a polynomial, this graph matches what we would see from 5.1. And then here's me plotting some extra points. So you can see if I plot -3, I got a positive y value of 45. And if I plot -1 right here, I get a negative y value. If I plot +1, I get a negative y value, right? Those are the two that we had right here. And then if I plot x equals 3, I get another y value that's positive. So since I'm looking for where y's are negative, right, I'm really looking at this piece of the graph down here. And I can see excuse me, that's corresponding to these two intervals. So from -2 to 0 and from 0 to 2. Right? And the reason that I'm not picking these two intervals as my solutions is because I'm allowing equal to 0 as a possible solution to this inequality. So right at x equals 0, I'm allowed to include that in my inequality. Because if I plug 0 into my inequality down here, I would get 0 is less than or equal to 0, and that's a valid solution. So I'm going to actually include x equals 0 in the entire solution interval. And so here's my solution as an inequality, and here's my solution as an interval notation. So this is basically going to be the process we go through for all the problems in this section. When we solve an inequality that's polynomial or rational, we're going to set it up in this fashion. We're going to go through this algorithmic process. Now, what if we take the same inequality that we have here and we remove the or equal to sign, right? How's that going to change the solution here? Okay. So let me just go to the next slide here. Say, suppose we change the inequality to be a strictly less than, right? And let's just bring back up all the work that we did. So here's the point plotting that we did, plotting x equals -3, x equals -1, x equals 1, and x equals 3. So we plotted those values, found what they are, and then I did graphing on Desmos this time. So I just plotted x equals -2, x equals 0, x equals 2. Right? And again, I just was highlighting the x-intercepts to point out to ourselves that at x equals 0, the y value is equal to 0. And so for the case of this inequality, I don't want or equal to 0 to be part of my solution set. So in this case, I'm only going to look between -2 and 0, and I'm not going to include x equals 0. So I'm only going to look between -2 and 0. Between -2 and 0, my y values are less than 0. And then between 0 and 2, my y values are less than 0. So I'm going to strictly look at that interval and that interval there. Right? And those are my solutions in interval notation. Okay, and then so again, the reason that I bring this up to you is it's just important for us to pay attention to, are we including or not including? Okay? All right, let's take a look at another example. Suppose that I have the inequality x to the 4th is greater than x. So if I'm going to solve this inequality, again, I'm going to want to subtract this x to the left-hand side and get 0 on one side. And I do that. And then step 2 is to set this equal to 0 to find the x-intercepts. Right? So if I was graphing this polynomial, I'm going to find the zeros and find the x-intercepts. So we do that. And in this case, I can factor out a common x. So I do that. And then I notice here, this is kind of unique. We don't see this very often. This is a difference of 2 cubes. This is x cubed minus 1 cubed. So just to remind myself of how that would factor, right? X cubed minus 1 cubed would be x minus 1 times x squared plus 1 times x plus 1 squared. So I'm going to plug into that formula, right? So here's my factored form. So I'm going to set each of these factors equal to 0. If I set x equal to 0, I'll get x equals 0. If I set x minus 1 equal to 0, I'll get x equals 1. And then if I set this quadratic equal to 0, I'm going to get imaginary solutions. So there's no reals that come out of this factor. So we just have x equals 0 and x equals 1 as the intercepts for, that's the x-intercepts, right, the zeros for this polynomial. All right, so if I plot those on a number line, there's my two x-intercepts of 0 and 1, and then I'm going to go through the same game where I'm going to pick numbers around each value. All right, so I'm going to pick a number to the left of 0. I pick -1. I plug it into my polynomial of x to the 4th minus x. I get a y value of 2. Pick a number between 0 and 1. I'm going to pick 1/2. Plug it into my polynomial. I get a negative value. And I'm going to pick something to the right of 1. I picked x equals 2. Plug it in, and I get a positive value. All right, so again, if I take a look at the graph, excuse me, here's my 0 of x equals 0. And here's the 0 of x equals 1. There's my two x-intercepts, right? And I can see to the left of x equals 0, I have positive values, right? So here's where the graph is positive. See, between 0 and 1, I'm going to have negative values. So I can see right here, between 0 and 1, on my x-axis, I'm having negative values. And then I can see to the right of x equals 1, I'm going to have positive values. And that's what I see here visually as well. So for this particular problem, we were wanting the polynomial to be greater than 0, right? So that corresponds to this piece, right, which is all of this here, so -infinity to 0. And then that corresponds to this piece where the graph is above the x-axis, right? So from 1 out to infinity for my x values. And that's this interval. So again, that's the same basic process. So basically what we're doing, again, is we're blending, if you will, the process of graphing the polynomial. We're looking at it visually, and we're solving the inequality in that manner. All right, let's look at one example where we have a rational inequality. So here's a rational inequality. So again, I want to point out to you, right, this is rational because I have a rational function, right? So I have a fraction, I have x in the denominator. So these are vertical asymptotes like we talked about back in 5.2 and 5.3. So I'm solving this rational function greater than 0, right? So just like last time, right, I'm going to get 0 on one side and everything else on the other. And in this case, I already have 0 on one side. So nothing that I really need to do there. And then the second step would be to find the zeros of the numerator and zeros of the denominator. So I want to find out where the function is undefined, and I want to find out where the numerator equals 0. So I'm literally going to set the numerator equal to 0, and then I'm going to set the denominator equal to 0. And those are going to be the points I plot on my number line. So I got -3 comes out of the numerator, +2 comes out of the numerator, and +1 is a 0 of the denominator. So those are the 3 points I'm going to plot on my number line. So here's the 3 numbers I'm plotting on my number line, and then again I'm going to play that same game. I'm going to pick a number to the left. I'm going to pick a number to the left and plug it in and see what I get. I'm going to pick a number between, plug it in and see what I get. Pick a number between here, plug it in and see what I get. And pick a number to the right, plug it in and see what I get. So to the left of -3, I picked -4. I plugged it into my rational expression and I got a negative number. I picked a number between -3 and 1. I picked x equals 0. I get a positive value when I do that. Between 1 and 2, I picked 1.5, right, 3/2, plug it in, get a positive value. And then to the right of 2, I picked 3, plugged it in, and get a negative value, right? So again, as a reminder, I'm interested in where the function is greater than 0, where it's positive. So I'm interested in these two intervals here. So I'm going to be looking at the interval -3 to 1 and the interval 1 to 2. Right, and again, if I look graphically here, right, it's negative to the left of -3. So here's -3. To the left, I can see the graph is below the axis. It's negative. Between -3 and 1, the graph is positive. So between -3 and 1, the graph is above the x-axis. Looks good. Now, x equals 1 is a vertical asymptote, right? So at x equals 1, there's a vertical asymptote. So notice in our solution set, we can't include x equals 1. Right? X equals 1 would cause division by 0. So I put an open hole there. And then from 1 to 2, the graph again is positive and above the axis, right? Like we saw right here. So then from 1 to 2, we're including that in our solution set. And then obviously from 2 out to infinity, the graph is below the x-axis and is negative here. So we're only wanting where the graph is positive. That's these two intervals. And then we're going to make sure we don't include x equals 1 in the interval because that's a vertical asymptote, right? I can't have, undefined being greater than 0. That doesn't make any sense there. All right, so this is basically what we're going to do in this section. We're going to solve inequalities that involve polynomials and rationals. We're going to blend our graphing analysis with the technology. Right? We're going to kind of use our graphing analysis and our technology together hand in hand to solve these inequalities. As always, if you guys have any questions, please post on the discussion board or Blackboard, and I will see you in the next video.